Hello everyone, now we're going to solve Cambridge IGCSE Physics, May June 2025, paper 4-3. Number 1. A car travels at a speed of 20 meters per second. The driver applies the brakes when he sees a red traffic light. Figure 1.1 shows the speed time graph of the car. A. Determine the speed of the car at 2 seconds. So you can just look at the graph, 2 seconds, trace it like this. And this is 11, 12, so 11.5. Don't forget the units, meters per second. B. Calculate the distance between the car traveled by the car between time 0 and 4 seconds. So in speed time graph, distance is the area under the graph. So you can write distance equal to area under the graph. And this is the shape of a trapezium. So it would be 1/2. A is 0.5. Plus B is 4 into height is 20. So that would be 45 meters. C. Calculate the deceleration of the car between time 0.5 and time 4 seconds. So in speed time graph, you can get the deceleration by calculating the gradient. So you can write deceleration equal to gradient. So we can take any 2 points that we like. I think the easy one is here 0.5, 20 and 4, 0. So m is equal to 0 minus 20, and 4 minus 0.5. That will be 20 divided by 3.5. So be around negative 5.714 and so on. So you can write 5.7 meters per second squared. Two significant figures. We don't put the minus here because it already says deceleration. If this says acceleration, then we have to put negative. 2. Figure 2.1 shows a space vehicle which consists of a capsule and a nose cone. The space vehicle is moving at a velocity of 7,800 meters per second. The mass of the space vehicle is 840 kilograms. Show that the momentum of the space vehicle is approximately 6.55 into 10.6 kilograms meter per second. So momentum is just mass into velocity. You can plug those in to the equation. Mass is 840 into velocity is 7,800. If you do that, you get 6552000. So just write that as the given one. 6. The capsule ejects a nose cone as shown in figure 2.2. Determine the velocity v of the capsule after the nose cone is ejected. Give your answer to 3 significant figures. So we know that total momentum, this is going to use the conservation of momentum, right? So total momentum before, you can write collision, but I don't see this as a collision because it's going to go apart. So before and total momentum after. So before is this much, right? 6.5 into 10 power 6. And for after, they are going in the same direction as well, so this will be positive. And we need to find the v, right? 720 into v plus 7850 into 120. So to get v, we can just do it like this. So 7850 into 120 is 9420. This will be divided by 720. So if you put that in calculator, you will get 7,788.88 and so on. So you can take three significant figures. So 7790 meters per second. See, a different space capsule returns to Earth. Figure 2.3 shows this capsule just before it lands in the sea. The capsule travels at terminal velocity. So the question is saying that there is no acceleration, and that all the forces acting on this will be like cancel out, because there will be no resultant force. The upward vertical force acting on the capsule is 120 kilonewtons. Calculate the mass of the capsule. So I just mentioned, right, there will be no resultant force, but it says upward vertical force is this much, so there has to be a downward vertical force trying to oppose this. So this downward vertical force is apparently weight. So it's just given that this is the weight of the capsule. So W is equal to mg. We can calculate the mass. 120 zeros divided by 9.8. That is 12244 point something. So we can take two significant figures, 1.2 into 10 power 4 kilograms. Figure 3.1 shows an archer aiming an arrow at a target. The archer pulls back on the bowstring, doing a total work of 110 joules of work. Her hand moves a distance of 0.45 meters. The bow is bent and stores energy. Show that the average force applied by the archer in pulling the string back is approximately 240 newtons. So we know the equation, right? W is equal to Fd. And this distance is in the distance of the direction of the force. So force, we want to find the force. Distance is 0.45. This is 110. So if you divide 110 by 0.45, you get F is equal to 244 point goes on, and that is approximately 240 newtons. B. The archer releases the bowstring. All the energy in A is transferred to the arrow. The arrow moves off at an initial speed, v. The mass of the arrow is 0.030 kilograms. 1. Calculate the initial speed of the arrow. So it says all of the energy will be transferred to the arrow. So that means that the arrow, the initial kinetic energy will be this much. So EK is equal to 1/2 mv squared. This is 110. 1/2 mass is 0.03 to v squared. So V is equal to 220 divided by 0.03, and you take the whole square root. That would be about 85.63, and if you take two significant figures, you get 86 meters per second. To explain why the speed of the arrow as it hits the target is less than value in B1. So along the whole process, right, the kinetic energy will not be constant. So this energy will have to be transferred to the surroundings. It will be lost to the surroundings because of the air resistance. You have to do work against friction or air resistance. The energy will be lost there. So you can write something like energy is lost to the surroundings while doing work against air resistance. For figure 4.1 shows a pen with the copper base on a hot plate. The hot plate heats the pen and the water. It explains how thermal energy is conducted through the copper base. So copper is a conductor, which means it has, so I'll just write it. Copper is a conductor which contains lots of free electrons that can move around to carry the energy through the metal. It collides with ions and other electrons to transfer the energy. Lattice ions also vibrate and cause the neighboring ones to vibrate to transfer the energy. B1, define inward specific heat capacity. So specific heat capacity is the energy transferred per unit mass to change the temperature by 1 unit. So if you forget about this, you can always go back to the equation, right? You figured this out, right? M delta T. So energy transferred per unit mass per unit temperature. To a student heats a metal object to 100 degrees Celsius. The student places the metal object in an insulated cup containing water at 22 degrees Celsius. The final temperature of the water and the metal object is 31 degrees Celsius. The specific heat capacity of water is 4.2 joules per gram degree Celsius. The mass of the water in the insulated cup is 50 grams. The mass of the metal object is 54 grams. Calculate the specific capacity of the metal. So before we do anything, we can write the equation down. Delta E by m delta T. So we need the change in energy, and then change in temperature. So firstly, it has 100 degrees Celsius, and the water has this much. The final temperature of the water and the metal object is 31 degrees Celsius, which means that the change in temperature would be 69 degrees Celsius, and you have mass and you need the change in energy. So how we get the energy is that energy loss by this metal will be equal to energy gained by water. So if we want to calculate the energy gained by water, we have specific capacity, mass is 50, change in temperature is 9. So this is how much the metal is lost in terms of energy. So that is 1890. And then, so if you want the C, 1890 divided by mass is 54 into 69. That will be about 0.507 to so on. So if you want two significant figures, you can write 0.51 joules per gram degree Celsius. Figure 5.1 shows 4 rays of red light P, Q, R, and S coming from a spotlight in a swimming pool. A defined in words refractive index for a ray of light traveling from air to water. So refractive index is the ratio of light in two different medium. In this case, it will be air and water. B, on figure 5.1, draw the paths of rays P and Q at the water-air boundary. So this is like going along the normal. So we'll just continue like this. Will not refract. Now this is this is boundary, and then light will travel faster in air, so it will bend away from the normal. So don't forget the arrows as well. See, the angle of incidence for ray R is 49 degrees, and calculate the refractive index of the water. So you can see that the refracted ray is going along the boundary, which means this incidence angle will be the critical angle. So this is the critical angle, and is equal to 1 by sine IC, 1 by sine 49. So n is equal to 1.325, so on. You can write 1.3. There is no unit for refractive index because it's just a ratio. D, explain why ray S is totally internally reflected at the water surface. Because apparently the angle of incidence is greater than the critical angle. And another factor is that it is traveling from more dense to less dense material. So those are the two conditions, right? So firstly, the angle of incidence is larger than the critical angle. The ray is traveling from more dense to less dense material. 6. Ultrasound is an example of a longitudinal wave. Define the term ultrasound. So it is like any sound that is higher than the largest human hearing frequency. So we can write sound with a frequency larger or higher than 20 kilohertz. B. Describe what is meant by a longitudinal wave. So the vibrations of the wave particles are parallel to the direction of wave travel. C. Ultrasound is used to locate objects below the surface of the sea. 1. Describe how ultrasound is used to locate an object below the surface of the sea. You may draw a labeled diagram as part of an answer. So we use the concept of ego when we use the ultrasound, right? So let's just say this is like a boat and you emit ultrasound, and then this is an object right here, and you know the speed of the sound in the sea, and then you can measure the time taken. So if you have those, you can calculate for the distance. V is equal to d by t. So this will be the distance, and as you gonna emit the sound, it will reflect back, and that time t would be 2t, right? Because it's an echo. Yeah, if we write this in letters, we can write like the emitted ultrasound waves are reflected of the object of the surface of the object, time taken for the waves to travel back and forth is measured. So we can see that distance is equal to speed divided by time, because this time is for both journeys. We can divide this by 2. To state one other use of ultrasound, it can be used for medical screening. Because it can like pass through the soft tissue, right? It also uses a similar concept with reflection to kind of create an image of the organs inside the body. So right, medical screening. 7. A student sets up the circuit shown in figure 7.1. A. Determine the value of the current measured by the ammeter. Now the ammeter is here, and you have 0.50. So same throughout the series circuit. B. Calculate the potential difference across the 6.0 ohms resistor. So we can use the equation, right? V is equal to IR. I is 0.5. R is so will be 3.0 volts. C, show that the potential difference across the 20 ohms resistor is 9.0 volts. So voltage is shared between components in a series circuit. So this whole thing is 12 and this get 3. So this means that this whole parallel connection will get 9 volts. And in parallel connection, you have voltages going to be the same. So you can view this as just two different items. So 12 minus 3 is equal to 9 volts. D, calculate the resistance of resistor R. So how can we do this? Well, we have this whole voltage and then the current, so we can calculate for the resistance of the whole circuit, right? So resistance of the whole circuit will be 12 divided by 0.5, which is 24, and that will be the total resistance. The first one has 6, and then you have to find the resistance of this parallel connection, which will be something like, okay, so 1 by R is equal to 1 by 20 plus, okay, so this R, so I'll write just RT, 1 by R. So my RT is, this is the RT, has to equal to, RT is equal to 80. So 1 by 80 is equal to 20R, R plus 20. So 18R plus 360 is equal to 20R. So 2R is equal to 360. So 1R is going to be 180 ohms. 8A1. State what is meant by an electric field. So electric field is a region where an electric charge experiences a force. 2. Figure 8.1 shows a negative point charge. On figure 8.1, draw 4 field lines to show the pattern and the direction of the electric field due to the negative point charge. So 4, you have to make sure that they are equally spaced, and we need to show the arrows as well. Arrow would be towards, because it is negative, right? It will be attracted by the positive charge. And remember that this the direction of electric field is the direction of force on a single positive charge. So B, the potential difference of a lightning strike is 2.9 to 10.8 volts. The energy transferred by the lightning strike is 4.5 into 10.5 megajoules. Calculate the charge that flows. So we have this equation, right? V is equal to, potential difference is just work done per unit charge. So work done is 4.5 into 10 power, this is 10 power 6, so I just write 10 power 11 divided by 2.9 into 10 power 8. So if you put that in calculator, you get 1551.7, and if you take to two significant figures, it is 1600 coulomb. See, the current in a lamp is 2.0 amperes. The lamp is switched on for a time of 120 seconds. Calculate the charge that flows. So Q is equal to IT. I is 2, T is 120, it's still in seconds, so you don't need to change the unit. So 240 coulomb. A figure 9.1 shows a transformer. 1. There is an alternating current in the primary coil. Describe how an alternating current is produced in the secondary coil. So this is just like asking for the operation of a transformer. So we can write that the alternating current in the primary coil produces change in magnetic field. This is transferred to the secondary coil via ion core. This magnetic field will be kept by the secondary coil, so EMF is induced. So just to give a brief summary, there is an alternating current, and that current is also cut by this primary coil, and the alternating current already produces a change in magnetic field, so this ion core will help to transfer that to this side, secondary coil, and because this coil will cut the magnetic field, it will induce the EMF. A step-up transformer has a turns ratio of 1:20. The voltage across the primary coil is 12 volts. Calculate the voltage across the secondary coil. So we have this equation. Vp divided by Vs is equal to Np divided by Ns. And because it is a step up, right, you already know that the secondary coil will have more turns. So this is for secondary coil. So if you want Vs, okay, this is 120, this is 20, and that Vp will be 12. So Vs is equal to 12 into 20, that will be 240 volts. B. The power lost in a cable is 1.25 into 10 power negative 3 watts. The resistance of the cable is 0.050 ohms. Calculate the current in the cable. So power loss, the equation is I squared R. So we want the current. I square will be equal to, let's just write I is equal to square root of power is 1.25 into 10 power minus 3 divided by 0.05. So you get 158. Oh wait, sorry. 10 power minus 3, 0.15811, and you can take two significant figures, 0.16 amperes. C. State two advantages of high voltage transmission. So if there is high voltage, then you can see that this current will be low because of the P is equal to IV. So if voltage is high, current is low, so this power loss will be low as well. So you can write first thing, there is less power loss, and because of that you can use thinner cables. Thinner cables usually have a lower resistance, but we don't really need to worry about more power loss anymore because it is already low, right? So firstly we can write there is less power loss. We can thinner or cheaper, let's just write thinner cables can be used. (10a) Define a light year in words. So light year is a distance traveled by light in 1 Earth year. B. It takes light 490 seconds to travel from the sun to the earth. Calculate the distance from the sun to the earth. So distance is equal to speed into time. Speed is 3 into 10 power 8 meters per second. So 490, we don't need to convert any units. 490. So that'll be 1.1470 into 10 power 8. So that'll be about 1.5 into 10 power 11 meters. C. Figure 10.1 is a scatter graph showing how the speed of galaxies moving away from the Earth varies with their distances from the Earth. The scientist draws a best fit line on the scatter graph, uses best fit line to determine a value for the Hubble constant. So we know the equation V is equal to H naught D. H naught is equal to V divided by D. So in this case, that will be the gradient, right? Because in the y-axis it is the speed, and x-axis it is the distance. So Hubble constant, gradient. So we can take any two points that we like. So an easy one would be around here, 80, 2, and then like 0, 0, 0. So m is equal to 2 minus 0, 80 minus 0. That is 0.025. You know, you have to look at the units as well. That would be 0.025 into 10 power 4 divided by 10 power 20. So that would be 10 power minus 18. Yeah, this is minus 16. This is 2.5 into 10 power minus 2. So that would be 2.5 into 10 power minus 18. This is the Hubble constant, and don't forget the unit, which is per second. So we can just write it like this. The speed of a receding galaxy can be estimated using redshift. Describe what is meant by redshift. So redshift is the the increase in observed wavelength of electromagnetic radiation coming from distant galaxies that are moving away from the Earth. 11. Define the half-life of a radioactive source. So half-life is the time taken for half of the radioactive material to decay. B. A protactinium nucleus decays into a uranium nucleus by the emission of a beta particle. Complete the nuclear equation of the decay. So uranium U. We leave the numbers for a second. Beta particle is 0, -1 because it's an electron. So we can match the numbers. So this will be 92. 92 minus 1, 91. And this will still be 234. To state the change that occurs in the nucleus during the decay. So the change is that one neutron changes to a proton and an electron. This is emitted. C. A different element decays by the emission of an alpha particle. Give 2 reasons why alpha particles are more strongly ionizing than beta particles. So ionizing means that they want to interact with other particles more, right? And that is because they have a greater charge. When a particle has a greater charge, it has more tendency to interact and react with other particles. So alpha particles have a greater charge, and they also have greater kinetic energy. So alpha particles have greater kinetic energy. So this is the end of the paper, and good luck with your studies.